Okay. So, yesterday we were discussing this theorem, and theorem was, suppose f is bounded on the closed interval a b and f has only finitely many points of discontinuities on the closed interval a b, and alpha is continuous at every point at which f is discontinuous, then f is Riemann Stieltjes integral. So, actually what he says is that if f is given to be a bounded function, but it has a point of discontinuities over the interval a b and the number of the discontinuous points are finite, and alpha is such which is continuous at the point where the f is having point of discontinuity, where f is discontinuous, alpha is continuous. Then in that case the function f will be a point of the class R alpha, that is the Riemann integrable Stieltjes integrable function with respect to alpha. So, in particular when alpha x equal to x, then you can say every bounded function which has a finitely many discontinuous points over the interval a b must be a Riemann integrable functions. And we have started the proof also. The proof what is given is the f is a bounded function. So, we can take the supremum value of f x over the interval a b as suppose m. This is over the interval a b. Okay, this one, and let epsilon be greater than given. Now, suppose E is the collection of those points where the function has a discontinuity, and this E is finite. So, let these are the points where the function has a point of discontinuity. Since they are a finite number, so we can enclose them by means of a intervals u j b j, closed intervals like this, and the length can be chosen very small sufficiently because these are singleton points. Okay. And all these subinterval is a part of the interval a b. Now, since alpha is continuous at the point this point, so by definition if we take any epsilon greater than 0, then the image of the alpha x when x belongs to this interval must lie within this epsilon neighborhood. So, suppose there are n subintervals, n points where the function f is discontinuous. So, we are getting n subintervals of this type, and if we choose the epsilon as epsilon by n, then over each one we can say this is less than epsilon by n, and total sum of the alpha will be less than this alpha b j minus alpha u j sigma of this sum of the corresponding difference can be made less than epsilon, because alpha is continuous. So, once it is alpha is continuous, we can make this for given epsilon, we can choose the delta sufficiently small number, say delta 1, delta 2, delta j n, says n, such that whenever the point is there, it will be lying between alpha by epsilon, then epsilon plus epsilon plus epsilon, total is epsilon by n, and total is less than epsilon. This we can do it with the help of the continuity of alpha. So, this was the discussion. Now, what we do in second case, that we will place these intervals which you have chosen u j b j in such a manner over the interval a b that the point of the discontinuity of f lies within these intervals, Okay. So, let us place this, or you can say that if we take a point E intersection a b, the E intersection a b is set of those points which are common in E and a b. E is the set of those points where the function is discontinuous. So, basically we are choosing all the points where the function is discontinuity within the subintervals u 1 v 1, u 2 v 2 or u n v 1. In one of the points we will get, all the points will lie within this like that. Okay. So, lies in the interior of the clear. So, up to here we have discussed it. Now, what we do is in the step 3 we remove the open interval, remove the segment u j b j from the closed interval a b. It means what we are doing is that this is our interval a b, okay, and here is the point say u 1 b 1 u 2 sorry u 1 v 1 u 2 v 2 and like this. Suppose these are the points say like u n say v n. Then what we do is we are removing this portion we are removing. So, we are getting now after removing a into u 1 a u 1 this one, then start with b 1 u 2 and like this, then start with v 2 and continue this way and up to here say v. So, this set K which is in which these things are not available, Okay. So, this set K forms a compact set. So, once we remove the segment u j v j from it, then the remaining set K is compact, because it is a finite union of the compact closed and compact set intervals like this. So, it is a compact set, compact or compact set is okay. Now, function f is given to be continuous. Since f is continuous over k, because the point of discontinuity we have already removed. So, f is continuous over k and k is compact set. So, every continuous function on a compact set is uniformly continuous. So, f will be, so f is uniformly continuous, function on k, uniform continuous function on k, clear this one. So, by definition what is a f is uniform means, so for a given epsilon greater than 0. So, for given epsilon greater than 0 there exists a delta which depends only on epsilon, not the point greater than 0, such that the mod of f s minus f t, this will remain less than epsilon if s belongs to k, t belongs to k and mod of s minus t is less than delta, by definition of the uniform continuity. Okay. Let it be 1. Okay. Now, let us partition the interval a b as follows. Suppose P is the partition, let P is the partition x 0, x 1, x 2 say x n of a b. Then B takes such partition that each u P is a partition where u j, each u j occurs in P, each b j, each v j occurs in P, means this u 1, u 2, u n, v 1, v 2, v n, these are the one of the points of the partitioning point of this interval a b, and no point of any segment u j comma b j, this open segment occurs in P. This is the restriction we are putting. We are choosing the partition in such a way that the corner points of these subintervals which are covering the point of discontinuities are basically coinciding with the partitioning point, but none of the point in between inside this interval are the partitioning point. are the points of the partition. This is one thing. Second thing is, in case if x I minus 1 suppose is not one of the uj, because this may be possible, the number of the points are finite, maybe the number of points are not as sufficient as the partitioning point is there. So, some of the x i's will remain untouched. So, if x I is not one of the uj, then what we do is, then we put the restriction A that the x I minus 1, that is the delta x I, this should be less than delta. This is our restriction. Okay. So, once you have partitioning this point, it means okay, now we get this. So, this is our x naught, x 1, x 2, x 3, x n and so on. Say this is A, this is B. Okay. And then we are coinciding this, say suppose u naught, u 1 and so on continue. Suppose here is u j, and after this we are not getting anything, and the points in between u j are not there, one thing. So, let us see, suppose we take any interval, clearly over any subintervals m I minus small m I, this will remain less than equal to 2 m. Why? Because what is our m? M is the supremum value we have chosen. This is m is the supremum value over interval. So, if I consider the x I minus 1, clearly because over the interval over x I minus 1 to x I, the minimum value of the function is m I, supremum value is a. So, m I as well as small m I both are less than equal to m. So, m I minus m I is less than equal to 2 m. This is true for each I, for every I, this is 2. And further, if x I 1 is not one of the point, if x I minus 1 is not one of the point of u j, unless this is not one of the point, then the difference between m I minus small m I, this difference can be made less than equal to epsilon by, because of this part, because function is continuous as well as uniformly continuous over the k. So, if the point x I minus 1 less than delta, if this is because we have put this, if x I is not one of the point, then this difference is less than delta. So, because of the one, this difference should be less than epsilon. So, m I minus small m I will be less than epsilon. Okay. So, that for each one is will be less than equal to epsilon. Hence, if we construct the proof upper sum minus lower sum. So, upper sum of the function f with respect to alpha over the partition the p minus lower sum of the function f with respect to alpha over the partition p. This is basically what sigma I is equal to 1 to n, say m I minus small m I into delta alpha I, which can be break up as sigma over k plus sigma over a b minus k, because the dropped interval, okay, this which are dropped. So, in this case is over k, this is less than epsilon, this is less than epsilon. So, we get epsilon into sigma of this part, but sigma of this delta alpha I is 1 to n is nothing but the alpha b minus alpha a. So, this will, and this part over this already we have function is bounded. So, m I plus m I is less than equal to 2 m, and since sigma of alpha I, alpha b minus this total is less than epsilon, this is because of the continuity, this sum of this corresponding is less than epsilon. So, we get from here is that this is less than epsilon. Okay, and this part will be epsilon alpha b minus alpha a plus 2m epsilon. But epsilon is arbitrary, but epsilon is arbitrarily small number. So, this shows that the right hand side will go to 0 and the left hand side. So, f will be the element of f alpha. This is what proves that. Okay. So, this is what proves. Now, another results also which is interesting. The result says suppose f is in R alpha on the closed interval a b, Riemann Stieltjes integral with respect to alpha over the interval a b, and f is bounded function bounded by say m in capital M. Phi is continuous on the closed interval m and capital M. This is phi. Then and h x is phi of f x on the closed interval a b, on the closed interval a b. Then this result says the h belongs to R alpha, that is Riemann Stieltjes integral on a b. So, if function f is Riemann integral function and phi is a continuous function on the that is the where the function have a range set, range of the set f is interval, then the composition of this function, continuous image of a Riemann Stieltjes integral function will be Riemann Stieltjes integral. That is what it says. Okay. So, this is just like that. Here we are taking this function, this is our interval a b, function f is given. So, here is our m and capital M, where the function f is attains the minimum and maximum value, and over bridges the function h is defined. Okay. So, what is a, when you combine the h composition phi composition f x, then it will transfer directly from here to here, which is h composition h x equal to phi composition f x. And if this is in R L, this is this function phi, oh this is phi, sorry, this is phi, and if this phi is continuous and this is in, this is continuous, this is in R L, R alpha, then our h will be in R alpha. That is what it says. Okay. So, let us see the proof of it. Choose epsilon greater than 0. Okay. Now, given that phi, since phi is continuous on the closed interval m and capital M, so it will be uniformly continuous. Uniformly continuous over this interval m and capital M, because every continuous function over a compact set is uniformly continuous. So, by definition epsilon we have already chosen. So, let us choose the delta. So, for this epsilon greater than 0, which is chosen earlier, there exists a delta greater than 0 such that, now I am putting the restriction on this, delta is smaller than epsilon, because this is any delta is true, then all the delta which are less, putting delta to be less than epsilon, this image will go there. Okay. So, let us take the delta to be less than epsilon, and phi of s minus phi of t is less than epsilon if mod of S minus T is less than or equal to delta. What it says is, for the, because phi is uniformly continuous. So, for any epsilon greater than 0, there will exist a delta such that image of this any point in which satisfy this condition must fall within this range. Now, suppose I take delta which is greater than epsilon, then I can pick up another delta which is smaller than this, less than epsilon. So, again this image will fall here. So, nothing, we are not losing anything, but it will be advantageous while proving the whole theorem. Okay. Now, further, since f is given to be an element in all alpha, so by definition the result a necessary and sufficient condition for a function to be a Riemann Stieltjes integral, or if you in the class of this, if there exists some partition for a given epsilon, there exists some partition such that upper sum minus lower sum is less than this. So, let f belongs to this, then there is a partition, say P x naught, x 1, x 2 and x n of A B, f A B such that the upper sum of the function f with respect to alpha minus lower sum of the function f with respect to alpha over the same partition is less than, say, delta square. Clear? So, this we are getting. So, let it be equation 2. Now, over the sub intervals we have, let x I minus 1, x I plus, this is the sub interval of this partition A B, this is the partition A B, this is a. Now, here the function attains this minimum value, say m I, and the maximum value is suppose capital M I. So, let m I and capital M I is the supremum of the function f x when x lies between x I minus 1 to x I, while the m I, small m I, is the infimum value of the function f x when the x lies between x I minus 1 to x I. Clear? Let be this one. Now, function h is defined, since h is defined, because whatever the result is, that h is, yeah, f is Riemann integrable, f is this, and phi is continuous function, phi is continuous on this, and h is a function which is basically phi of h f x. So, what are the range of f, h is defined on it. So, basically the h is defined on on m and capital M, this is. So, in this case when you partitioning this m, say m and capital M, and suppose I partition it, say m naught less than m 1 and so on, say here is m n equal to m. So, if we picked up the, say, m I minus 1 and m I. Now, in this case when you consider the upper and lower bound for the function h, then we say, we denote this as, let us denote, let m I star is the supremum value of h t. I am using the t, where t lies between m I minus 1 to m I, and small m I star is the infimum value of h t when t lies between m I minus 1 to m I. Is it not? Just I am taking this one. Now, so this is our interval A B. Here I am taking one, say, sub interval x I minus 1, and here is, say, suppose images. So, this is our, say, m I m, and here is capital M, say this is our. So, basically this will be the, Okay, all the functions will be somewhere here, clear. In fact, this is this one like this. So here is, now we are dividing here, and then h is defined over is defined on this side. Okay. Now let us choose the part. Suppose for I, divide the number 1, 2, 3 n into 2 classes. First class is A, 2 classes A and B, as follows. When I belongs to A, for I belongs to A, our choice of delta shows I belongs to A means, that is, if I belongs to A, for I belongs to A, or for I belongs to A, if, or just I belongs to A, if mi minus small mi is less than delta, and I belongs to B if mi minus small mi is greater than or equal to delta. So, this will be like this. Now, picked up now class 1. So, for I belongs to, so for I belongs to A, what is our choice? When I is in A, the mi minus small mi is delta. Okay. So, in this case, what is the mi star minus mi star, small mi star? This will be, because phi is what? Phi is uniformly continuous. So, if I belongs to A, it means it satisfies this condition. Once it satisfies this condition, then because the h or phi is defined on what? On this interval. So, it satisfies this condition. Therefore, the difference of this mi minus small mi star must be less than epsilon. So, since our I belongs to this, so our choice of delta shows that the mi star minus small mi star is less than, and this follows from this equation, that is the relation, I will say the relation is say x star. Okay. So, it follows from the relation star. Okay. So, nothing by this. So, first thing, and if for I belongs to B, where this is greater than equal to delta, we have in this interval the mi star minus small mi star is less than equal to 2 k, where k stands for the supremum value of the phi when t lies between m and capital M. So, just supremum value, and since it is greater than, so use the condition 2, where condition 2 is this condition we have taken, that is mi minus delta square. Where is that delta square condition? So, this is condition 2. This is our condition 2. This mi sigma of mi minus mi small mi delta alpha is less than delta square. So, use the condition 2. So, use 2. Then in that case, the u p f alpha minus L p f alpha. This is what? This is sigma mi minus small mi delta alpha I is 1 to n. But if we take and this is given to be less than delta square, this is given to be delta given. Now, if I take the only for sigma mi minus small mi delta alpha I over the set B only, then obviously it will remain less than delta square, because this sum is smaller than this. So, it is less than delta square, but this will be greater than equal to what? Over B, this is greater than equal to delta. So, it is delta sigma I belongs to B delta alpha I. Okay. So, what does imply? That implies that sigma delta alpha I when I belongs to B is basically less than delta. Let it be 3. Okay. Now, consider the partition. Now, consider the upper sum of the function h with respect to alpha minus the lower sum of h with respect to alpha, and this we can divide in two parts when I belongs to A, m I star minus small m I star delta alpha I, plus when I belongs to B, m I star minus small m I star delta alpha I. Okay. Now, see, this will be m I star minus a when I belongs to A. We have already justified this is less than epsilon. So, this is basically less than epsilon, and then delta alpha I will be remain less than the sigma of delta alpha I is nothing but less than alpha B minus alpha A. So, we get this part. Okay. The second portion is this entire thing is less than 2k, because this is 2k. So, it is less than 2k, and then over B the sigma is less than epsilon. Sigma is less than this delta alpha I when you choose what is it? Sorry, delta. Sigma is less than delta. So, it is delta. So, once it is delta, but delta is less than epsilon. This is our choice in the very beginning. Of this we have taken delta to be less than epsilon. So, we can choose the delta outside. So, we get the P h alpha minus L P h alpha is less than equal to epsilon outside. What you are getting is alpha B minus alpha A plus 2k. But epsilon is arbitrary. Since epsilon is arbitrary, so this shows that satisfy the necessary sufficient condition of that theorem. Therefore, H must be in R alpha, and that proves the results for it. Okay. So, that proves the results for it. Okay. Now, let us come to now as a we will not show that, but one note or result we will see, then proof we will see while going for the exercise. We will do the proof for this. The result is what this says is, suppose f is bounded on the closed interval a b, then f is Riemann integral on the closed interval a b if and only if f is continuous almost everywhere on a b. In fact, the concept of the almost everywhere, this is a concept which is given in the measure theory, measure integration. But what is the meaning of almost everywhere? Suppose a property holds everywhere except at some point, and that set of those points form a measure 0, then we say the property holds almost everywhere. That is, so here we mean the set of points where f is not continuous, forms a set of measure 0. Measure 0, it means the length of that set, measure of the set is 0, because when it is an interval, we say the measure of the set A is an interval. Interval means the B minus A, but if the set A contains the point of real numbers lying on the real line and they are scattered, you cannot say that the difference between the last point and the first point is the length of the interval. So, it cannot be a measure, it will be more value than whatever actually have. So, what we do here, that we find if in arbitrary set, for an arbitrary set, for any set A which is subset of R, the measure of the set A we define as measure of, this is out of course, just I want to measure of a set A is the infimum value of sigma length of I n is 1 to infinity, such that the countable union of I n covers A. So, what we do is we consider the intervals I 1, I 2, I n and open intervals where this interval covers the point of the set A. Then find out the length, take the summation and then change the interval again, take the infimum value. So, if infimum exists, we say it is the measure of the set A, where I n is an open intervals for it. Okay. So, this is what we, but we will not discuss in detail, but so whenever the set is function is continuous except at the point which forms a set of measure 0, then the function must be a Riemann integrable function. So, because every continuous function is Riemann integrable, but the functions which are even not continuous, bounded functions having a simple continuity point of discontinuity and those numbers are forms a measure 0, it will be a Riemann integrable function. So, that is what it is. Now, let us see some few properties of the Riemann Stieltjes integrals. We will list the proof property and proof 1 or 2 will be good enough. Now, if f 1 is a Riemann Stieltjes integral with respect to alpha, f 2 is a Riemann Stieltjes integral with respect to alpha on the closed interval a b, then the sum f 1 plus f 2 will also be a Riemann Stieltjes integral with respect to alpha, and C f will also be a Riemann Stieltjes integral for with respect to alpha for every constant C, and the integral a to b f 1 plus f 2 d alpha, the Riemann Stieltjes integral, the sum of it will be sum of the integrals f 1 d alpha plus a to b f 2 d alpha, and C times f d alpha is C multiplied by a b to b f d alpha. So, this is the first result. Second result says, if suppose f 1 and f 2 are the two Riemann Stieltjes integral, if f 1 and f 2 are the two functions such that f 1 x is less than equal to f 2 x on the closed interval a b, and they are also Riemann Stieltjes integral, and then integral a to b f 1 d alpha is less than equal to integral a to b f 2 d alpha. Of course, where f 1 and f 2 both are in alpha, all alpha. Okay. Third is third property is, if f belongs to R alpha, that is Riemann Stieltjes integral on the closed interval a b, and if a is less than c less than b, then f is Riemann Stieltjes integral on the closed interval a c as well as on c b. Means, if we divide that a b into two parts a c to c b, then over each subinterval function f will remain Riemann Stieltjes integral with respect to same alpha, and the value of the integral will be the sum of these two, and integral a to b f d alpha is the same as a to c f d alpha plus c to be f d alpha. Fourth property is, if f is a Riemann Stieltjes integral with respect to alpha on the closed interval a b, and if the function f x is bounded by m on the closed interval a b, then integral a to b f dx f d alpha into f d alpha modulus of this is less than or equal to m times alpha b minus alpha a. Okay, modulus of this d alpha. Then E property, if f is Riemann Stieltjes integral with respect to the monotonic function alpha 1, and f is a Riemann Stieltjes integral with respect to monotone function alpha, means f is Riemann Stieltjes integral with respect to the two monotonic functions alpha 1 and alpha 2 respectively are there, then f will remain Riemann Stieltjes integral with respect to the sum of these alpha 1 plus alpha 2, because if the alpha 1 and alpha 2 are monotonic increasing, the summation will also monotonic increasing. If they are monotonic decreasing, they will also be monotonic decreasing, and hence integral of f alpha 1 d alpha 1 integral f d alpha 1 plus alpha 2 over a to b is the same as a to b f d alpha 1 plus a to b f d alpha 2, and if f is Riemann Stieltjes integral with respect to alpha, and c is a positive constant, then f is Riemann Stieltjes integral with respect to c alpha, and integral of this a to b f d c alpha is c times a to b f d alpha. The proof of these results property follows by using the definition itself, but however, we will see the proof of first result only. So, let us see the proof for first, and rest will be following as usual. Okay. So, let f is f 1 plus f 2 and P is any partition of the interval a b, any partition of a. Then what we have? Now, let us see a lower sum of f with respect to alpha over the partition P is what? Is basically the sigma small m I delta alpha I is 1 to infinity, where m I is the infimum value of the function f x over x lying between x I minus 1 and x I. Now, if I take the two functions instead of f, we take the f 1 and f 2, then what happens is, and if f is the summation of f 1 plus f 2, then the infimum value of m I, this will be greater than equal to the infimum of the function f 1 x over that same interval x I minus 1 less than x I plus infimum value of f 2 x over the same interval x lying between x I minus 1 to x I, and the supremum will attain, and supremum of this f x will be, that is capital M I will be less than equal to supremum of f 1 x over same x over this interval plus supremum of f x, supremum of f x when x lies between x I minus 1 to x I. So, supremum of the sum is less than or equal to sum of the supremum and infimum will be greater. So, that is what using this criteria we have now. The lower sum of P f 1 alpha plus lower sum of f 2 with respect to alpha is less than or equal to the lower sum of the function f with respect to alpha because of this result. Okay? This result, and which is or lower sum is always be less than the upper sum. So, we get this, and then upper sum because of this is again less than or equal to what? Upper sum of P f 1 alpha plus upper sum of P f 2 alpha. This okay. Now, apply this condition. So, let it be say 4. Okay. Now, if f alpha since if f belongs to or f 1 belongs to all alpha and f 2 also belongs to all alpha. So, for a given epsilon we can find there all the partition by necessary insufficient conditions, all the partitions P j, where j is 1 and 2, P 1 and P 2 respectively, such that the upper sum of f j with respect to alpha over the partition P j minus lower sum of f j with respect to alpha over the partition is less than epsilon r when j is 1 2. This is by definition. Okay. So, use the now 4, use 4. So, what you are getting is, if we replace use 4, replace P 1 and P 2 by P, which is the union of this, a refinement of P 1 and P 2 partition. So, once we take this common partition, then 4 will imply, then 4 will imply what? Upper sum minus the lower sum. What is the upper sum minus lower sum? Upper sum P alpha minus upper sum minus lower sum is this. Now, upper sum in the first fourth, this is less than or equal to this and lower sum is greater than. So, when you take the minus time, you will come, you are coming like this. So, it is less than or equal to upper sum of P 1, this is P 1, P 1 f 1 alpha minus lower sum P 1 f 1 alpha plus upper sum of P 2, I think this I did upper sum P, okay, no, this is okay, upper sum of P P 1 is okay. So, we are getting this part is P 1 alpha, and then here we are getting this is less than or equal to what? Upper sum of P 2 f 1 alpha minus lower sum of P 2 f 1 f 2 alpha. From here just you get it like this. What you are getting is P j. Okay. So, if I take this, why it is so? Because upper sum decreases. So, P of this is less than or equal to sum of this, lower sum increases. So, we are getting this one, and this is less than epsilon, this is less than, so this is less than 2 epsilon. So, we are getting this is less than 2, which proves, which implies that our f, which is f 1 plus f 2 must be null alpha. Okay. That is all. So, we get there. prove this same, we have this one, therefore. And now for the integral part, we can say, for second part, we say with the same partition P, with the same partition P, we have the upper sum P f j alpha is strictly less than f j d alpha plus f sin alpha for j is 1 2. And because this upper sum infimum value is this integral, so we can get this thing. Hence, the second implies this part. Hence, second will imply that integral f d alpha is less than equal to u p f alpha, which is less than integral f 1 d alpha plus integral f 2 d alpha plus 2 f sin alpha, and f sin alpha is arbitrary. So, the result follows. Okay. So, this now another property is also which we just mentioned. If f is in R L and G is also in R alpha on the interval a b, then the product of this is in R alpha. Then second part is, if mod f belongs to R alpha and modulus of integral a to b f d alpha is less than equal to integral a to b mod f d alpha and less than equal to b. The proof is based on the previous. If phi is a continuous function, f is a Riemann Stieltjes integral, then phi composition a f will be a Riemann Stieltjes. So, depending on it. So, choose phi x or phi t as t square, which is continuous. Okay. And therefore, if f is R R, then it implies that phi of f x, that is the f square, must be in R R by Theorem previous. Okay. So, nothing to. Similarly, what is 4 f g? This we can say f plus g square minus f minus g square. Now, this is integrable, this is integrable, belongs to this. So, this belongs to this. So, this implies if f and g both are in R alpha, then the product f g will also be in R alpha, because the constant times of this are also in R alpha. So, this implies. Then further, if we take C as the plus minus 1, so we get what? C into integral f d alpha is greater than equal to 0. Suppose integral f d alpha is negative, then take the C to be minus. If it is positive, then you take this one. Okay. Then modulus of integral f d alpha is equal to C times integral f d alpha, because this is non-negative, and then this is integral C f d alpha, and this is less than equal to integral mod of f d alpha, because C alpha is less than equal to g. So, what we say is, so if our, so this implies that if mod f alpha belongs, mod f belongs to alpha, then the result hold. Then this result, that is integral modulus of integral a to b f d alpha is less than or equal to integral a to b mod f d alpha holds, and that is proof the results. Okay. So, this is all about the. Thank you very much.